Oh god. Okay. Hold on. Yeah, I think we're live. I'm gonna have to mute myself for a bit and the music just to check if the audio is doing okay. Hold on. Okay, audio is super. Desktop audio is super loud. Let's knock that back a bit. Maybe. Let's see. Probably that's good. Let's test it out again. I think this should be good now. Okay. Anyways, I'm trying, at least, to learn statistics from this book. It's called... Let me just remember, we're at page 54. I think this should be good now. Oh god, I forgot to mute myself. No. Okay. There we go. No more echo. Where were we? Biostatistics, the Bare Essentials, 4th edition. And we're currently at God, this is taking so long. Dude, isn't there a shortcut to like... Oh. Go to the next page. And then I just figured it out. It's the arrow keys. Right, we're at chapter 5, probability. Or was that page 56? Right. Why did we go to 92 all of a sudden? What? Okay, I'm not gonna mess around with that. Let's go there naturally. Nope, that's chapter 6. Oh god. I'm also still a bit sick and under the weather, so you'll hear a lot of coughing. Imagine you have an urn with 73 white marbles and 136 black marbles. What is the probability that if you took out 12 marbles, placing each one after you took it out, you'd have seen exactly 5 white and 7 black ones? That is some binomial stuff, which, you know, I once learned. I once knew how to do this exactly, but I'm gonna have to refresh a bit on all of these things now, because I need to know what I'm doing when it comes to research and everything else. I can't just, like, whenever I don't know something, just like shove it under the carpet and be like, it'll be fine, I can just hand wave my way through it. But getting to a point now where I actually need a good, not a super good, but just like, I should at least know the basic things, okay? So, refresher. I need a refresher on statistics. Anyways, I've worked out the first 4 chapters already. This is a pretty good book so far. It's pretty light, but not super light. Like, it doesn't go delve into the super theoretical stuff, but it's also not hand wavy either. So it's a good balance between the two. It's also very nicely written. A disclaimer: open up just about any other book on statistics and you'll find a long section on probability theory. It usually consists of examples such as the one above in setting the scene. The answer given by most students to problems such as this is, who cares? To us, they got the right answer. The 2 of us have been messing around with statistics for a total of about 90 years now. That's the 2 authors I think they're referring to. That's combined, not each. Yes, that would be crazy. Studying statistics since the moment you were born. And we can't remember when we've ever had to figure out a problem like this, except when we were wading through statistics text. Right, so like, these kinds of questions, you wouldn't encounter them like when you're doing statistics and research and stuff, you know? But, much of what's covered in such chapters is undoubtedly of great interest to those who are so inclined, but is of little direct value to the clinician. Instead, this chapter gives you what we think are the necessary survival skills to understand and deal with probabilities in situations you're likely to encounter. Anybody who wants to figure out the correct answer to this and other such problems should be reading another book. Also, you won't know how to answer these types of questions. Is this a real person? Or are they just trying to make a joke? Count Sahervom Masok. It is true. But he did not write a book on probability or anything like that. That this is where the term masochism does come from. It'll be a very, like, good coincidence for the writers of this book if this guy actually did write a book on probability, but yeah. That would have made the joke a lot better, but yep. What do we mean by probability? This is not as easy to answer as it sounds, but rather than getting bogged down in philosophical discussions, we'll rely for now on your intuitive understanding. Probability deals with the relative likelihood that a certain event will or will not occur relative to some other events. We can derive probabilities in one of 2 ways, empirically or theoretically. the empirical way. Each of us in our youth or second childhood has probably asked out for a date. A number of people. Dude, English. Wait, am I dumb or is this just a typo or something? Has probably asked out for a date. Asked to date. Just replace this with the word to. Asked to date a number of people of the opposite or the same sex. We've been accepted by some and rejected by others. Now we want to look back and see how we've done. Possibly as a guide to trying out our old skills. To keep things non-sexist and simple, let's say we can categorize our ASCIIs into 4 mutually exclusive types based on what it was that first attracted us to them. Their body, their mind, their wallet, and our desperation. In table 5.1 we put down how we did, allowing for some pedigree of poetic license. Wait, okay. ASCIIs are the person we asked out, right? And then... okay. What the percent success column tells us is how well we did in the past with each of these 4 types and gives us the probability of success in the future, assuming nothing has changed. The key point is that the probability based on past performance holds true now and in the future only under similar circumstances. If the circumstances have changed, we haven't been able to see our toes for the past decade, or those who had been the body class now have moved to the desperate, then the probabilities no longer apply. Right, let's check this out. So we asked 13 people out, and oh no, sorry. We asked 10 people out. Wait, no, we asked 50 people out. 10 of them, we are attracted to their body. And of the 10 people we asked, 3 of them accepted our proposition. So that's a 30% success. 23 people we asked were out of desperation. Is that right? Yeah, our desperation. So when we are desperate, our success is really high. Dude, I guess being desperate means you'd settle for anyone, even, I don't know how else to say this, but even lower people, and lower people are more likely to accept you, is the, I think, what the statistic is trying to convey here. Okay, yeah. Okay, we asked 5 people out because they're super rich, but only 1 of them accepted us. Which seems about right. If you're only after money, then you won't get super far. The classic example of empirically derived probabilities is the tout sheet sold for horse races. The odds they give, another way of expressing probabilities, are based on how well the horses did in races of the same length, under the same track conditions, ridden by the same jockey, and these days under the influence of the same drugs. Wow. Are you allowed to drug horses for better performance? I don't think so. I think this is just like a I don't know, comment on the corruption in horse racing. I don't know, but yeah, this book just like has these random comments about unrelated, off-topic things, which, you know, I mean, I I'll I'll welcome it. Like it takes me away from studying, like a little break, because you just get caught off guard. Almost all of the probabilities we encounter in the health field are derived empirically. For instance, the probability of survival for a cancer patient is based on the known survival rates of similar patients who have the same stage of disease and have undergone the same treatment regimen. Our definition also assumes that if any of these factors change, such as admitting patients at an earlier stage or changing what we do to them, these empirical probabilities go out of the window. Makes sense. The empirical way is also the basis for the old diagnostic dictum that if you hear hoofbeats, it's more likely to be coming from a horse than from a zebra. Horses are more common here than zebras. What do they tell medical students in Kenya? It's more likely coming from us. Oh my god, okay. Analogously, it's more likely or probable that the patient has a more common disease than a rare one. When we've gotten tired of losing our money on the nags and want to lose it some other way, we can always shoot craps at Las Vegas or Atlantic City. If you've ever been there, you'll have noticed that the craps table... Oh, craps is a game, yeah, I was like wondering what craps meant here, but I just remember now, craps is a game. It's like a card game or something. Is it a card game? Our knowledge of such matters is derived solely from movies and the reports of others, not from personal experience. Sure thing. The odds given for rolling a 7 or 11 on the first row or hitting a certain number are not based on the experience of the croupier. They're figured out based on the theory of probability. Take a simple example. Let's roll a dice. Each of the 6 sides has an equal likelihood of ending up on top, and which one actually appears is a purely random event. Consequently, the probability of rolling a 3 on this one toss of the dice is 1 in 6 or 0.1667. We don't have to do this experiment 1,000 times to find this out. We can get even fancier and calculate the probability of getting a 10 with one roll of 2 dice, of drawing an inside straight, or of rolling a 3 at roulette. 5-6. As a free bit of information, the payoff is always less than the calculated odds, with the exception of Donald Trump. Has any casino owner ever gone bankrupt? Wow. And the second bit of free information. The payoff at the tables is light years better than in state or provincial lotteries. Casinos pay an average of 50 to 80 cents on the dollar. Lotteries pay at most 10 cents on the dollar. Hey, so lotteries are a faster way of losing money than going to a casino. All of these calculations are based on our knowledge of the likelihood of occurrence of various chance events, which is the essence of probability theory, and that's what we'll be concerning ourselves with in this chapter. We want to emphasize that all of this is to make you better clinical researchers, not to lead you down the road of corruption by making you better gamblers. You can never win at gambling, man. Unless you cheat. Like, very cleverly cheat. By, like, marking or whatever. Except in Chicago, where they adhere to the motto, vote early and vote often. We haven't even reached 7 yet, I don't know why I'm reading it. Mutually exclusive and conditionally dependent events. To understand probability theory, it is necessary to differentiate between 2 types of events. Those that are mutually exclusive and those that are conditionally dependent. 2 events, X and Y, are mutually exclusive if the occurrence of one precludes the occurrence of the other. I think I know what precludes means, but I'm gonna double check. Preclude. Okay, if one event makes the other impossible, then those events are called mutually exclusive. The simplest event of this is flipping a coin. Heads and tails are mutually exclusive in that if the head side appears, the tail side won't, and vice versa. Which party a person votes for in an election for a specific office is a mutually exclusive event. However, how a person voted in the last election for all candidates may not be mutually exclusive. The voter may have voted for one party for some offices and for another party for other offices. Okay. Closer to home, respiratory acidosis and alkalosis are mutually exclusive events. If you have one, you can't simultaneously have the other. On the other hand, cardiac disease and esophageal reflux are not mutually exclusive. If a person has some chest pain and the ECG confirms the presence of an infarct, it doesn't necessarily mean the person can't have reflux at the same time. Two events, X and Y, are conditionally dependent if the outcome of Y depends on X or X depends on Y. Returning to the gambling tables, the probability of throwing a 5 with a single toss of 2 dice is 11.11%. There are 36 possible combinations, 4 of which yield a 5. However, if you throw the dice one after the other and the first die comes up 1, then the probability that the sum will be 5 is 1 in 6, or 16.67, because we have to get 4, and well, that's just 1 in 6. Since we're just looking for one particular number. That is the probability of a 5. Conditional on the first die being a 1 is 0.1667. Using the example in table 5.1, our overall or unconditional success rate was 30 out of 50. However, our hit rate with bodies was 30%, that is our success, conditional on the person being chosen for his or her body was 0.3. Dude, a 60% success rate is kind of insane. Turning to more mundane examples, we've all heard that the life expectancy of a person is somewhere around 74 years. But this doesn't tell the whole story. Women live longer than men, 78.1 years for white females born in 1980, as opposed to 70.7 years for white males born in the same year. Black people's life expectancies are about 7 years less than this. That's a lot, honestly. And all the figures are about 3 years more than for people born in 1970. The probability of a person living to be 80 is conditional on several factors such as gender, race, and year of birth. 3 years more the earlier you were born is kind of crazy, because you wouldn't have access to the technology and stuff if you were born earlier. So 3 years more is a bit insane. It would imply that as the years progress, we're getting less healthy, which I guess is true, but it should be counteracted by advanced medicine. At least it still is currently. Life expectancy is going up slowly everywhere around the world. The difference between mutually exclusive and conditionally dependent events is important because we have to figure out probabilities differently for each of them. Mutually exclusive events and the additive rule. To illustrate the difference between mutually exclusive and conditionally probable events, let's assume that the unit we work on admits only those patients with one of 3 mutually exclusive disorders. I'm not saying all of that. CTP, IHS, and ISD. So mutually exclusive, if you have one of them, you definitely can't have the other. Yeah. However, these conditions don't occur with equal frequency. CTP is relatively rare, and only 10% of our patients suffer from this, as opposed to 30% from IHS and 60% from ISD. Moreover, the proportion of males and females is different for each disorder. These are given in the third column of table 5.2. And what is the probability that the next person through the door has either CTP or IHS? I think these sound real, but let's actually check it out. Cryptogenic tinea pedis. It looks like something to do with the eye. Okay, that's just a foot infection. Tinea pedis. Idiopathic angnail syndrome. Iatrogenic systemic degradation. They were using like real terms. Like these words do have a meaning in the medical field, but I think they're just jumbled up together. They just jumbled up a bunch of medical terms to make it sound realistic, but I don't think it is. Because I can't find any information for iatrogenic systemic degradation. Oh, degeneration. Okay, hold on. That sounds like a terrible disease to have. Systemic degradation. Yeah, I mean, even if I've corrected it to degeneration, instead of degradation. I'm still not getting any search results, so yeah. Bunch of jumbled up medical terms. Anyways, this is just 40%. 0.3 plus 0.1. Yeah. Why do we add the probabilities rather than, say, multiplying them or taking their square roots? It may help if we think for a moment in terms of body-sensitive proportions. If there were a total of 100 patients in our wards, 10 would have CDP, 30 would suffer from IHS, and 60 from ISD. So the condition would be satisfied if he or she were one of the 10 from the first group, or one of the 30 from the second. In other words, 40 of the 100 patients would satisfy the condition and 60 would not. We can summarize what we've said by the additive rule. If x and y are mutually exclusive events, then the probability of x or y is the probability of x plus the probability of y. Obvious reasons this is called the additive law, put into formal jargonese. Wow. Yep, where PR is statistical shorthand for probability. Needless to say, we're not limited to just two events. The same law holds with as many mutually exclusive events as we want. Conditionally probable events and the multiplicative law. This is multiplication but for and. Yeah, if both will occur, then you have to multiply them together. Yeah, we're just gonna skim through this since I have a gist of what is being talked about. Probability of x and y equals probability of x multiplied by probability of y given that x occurs. Yeah, y given x. Just for practice, let's run through a few other examples. The probability that the patient is a female with CDP is the probability of CDP times the probability of being female given a diagnosis of CDP. Probability of a female with IHS is 21%. You figure it out for yourself. What? The probability of a female with IHS. $21 over here, and we can figure that out if we just say 100 multiplied by 0.3 is 70, no, oh, Jesus, what's wrong with me? 100 multiplied by 0.3 is 30, 30 multiplied by 0.7 is 30 multiplied by 0.7 is, yeah, 21. Right, permutations and combinations. Okay, many events are neither mutually exclusive nor conditionally probable. They are independent of one another. we were going to use the example of fitness for office and actually being elected to office. Oh my god, so many political statements. However, we quickly realized that this is more likely an example of mutually exclusive events. Oh my god. If you're fit for office, then you'll not be elected. And if you were elected, then you were never fit for office in the first place. These guys. Okay, problem arises when events that are independent of one another are mistakenly assumed by some people to be conditional. Let's say you're back in the casino standing over the roulette wheel. I know where this is going. This is gonna be the what it's called. What is it called? The gambler's fallacy. Yeah, you've seen that the last 5 numbers have all been red. Now, you know what? You know that, assuming the wheel is honest, red and black have the same probability of appearing, so half the numbers should turn up red and half black. What's the probability that the next number will be black? Yeah, the gambler's fallacy. The gambler's fallacy is thinking that the 6th roll is conditional on the previous 5, that after a long run of red, the probability of black is higher, so as to make the overall proportion of reds and blacks closer to 50%. However, the ball does not have a memory and has never studied probability theory. It doesn't know what the previous results were, and the probability of black is 50%. Exactly what it would be if the previous 5 rolls had also been black. Oh, blah 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 blah. Yep, we get it. Alright, as long as we're in the casino, let's see what other valuable lessons in life we can learn. If we're playing stud poker, where 5 cards are dealt to each person, how many different hands can be dealt? For the first card, there are 52 possibilities. After this card is gone, then there are 51, blah blah blah. It's 52 factorial. Which is that. Wait, that feels very little. That feels very small. Yeah, that's definitely wrong. Oh my god, I thought this was factorial, so I thought there was like multiply dots coming after the 48. Okay, so the actual 52 factorial is 8 with 67 zeros behind it. What was the question here? Oh yeah, if we're playing... Okay, 5 cards are dealt to each person. I thought it was an entire deck. Okay. N is the total number of objects in the set, which in this case is 52, the number of cards. And R is the number of objects that we're looking for, which is 5. We also need another term, which is N factorial. Yeah, we know that. So the number of permutations of n objects taken R at the time is... Okay, so this is the formula for permutation. Which, okay, makes sense. Which, thank the powers that be, which is mathematics. time now for a couple of definitions. First, that term permutation. Our result is the number of different ways 5 cards can be dealt. Oh, yeah. The order. Yeah, okay. So combination is the one that for the order doesn't matter, so we're accounting for order. It's just the same thing, but you have to divide by r factorial. Because, yeah. Basically, there are 120 copies of the same thing. So you have to divide it by that amount. Wait, not copies of the... Okay, for each... Yeah, so for each combination or sequence, there are 120 other equivalent sequences. So you have to divide the total sequences by 120 to get the unique sequences. With permutations, we're interested in the order in which the events happens. With combinations, the order is irrelevant. Just to drive the point home, if we were participating in a lottery in which we had to select 6 numbers out of 49 and the numbers had to be in a specific sequence, we'd be dealing with a permutation. If those 6 numbers could occur in any sequence, it would be a combination. The Ontario 649 is the latter. Just for fun, figure out the odds of winning. Bet you'll never play again. Here the exclamation means emphasis, not factorial. The law of at least one. Let's assume that 5% of the time a lab test from a perfectly normal person comes back labeled abnormal. That is, if we tested the serum rhubarb level of 100 barbic individuals, 5 could have results that indicate either hyper or hypohubarbulemia. What is the probability that if you order an SMA-12 on a completely healthy person, at least one of the 12 results will be false positive? think they're meant to be at times here. Yeah, there's definitely some mistakes. False positive. False positive is it's positive, but it's actually not. So that's 5%, but we're doing it 12 times. So, okay. At least one of them will be positive. So, let me think about this. So we have to use combinations. Wait, no, this... Okay, wait, hold on. Now we just have to get... We just have to do 1 minus... No. Or at least 1. So just 1 minus 0.95 times... Well, 1 minus 0.95 to the power of 5 is probably the right answer there. So that is 22.6%. Wait, did I... Oh, I did it to the power of 5. Oh my god, I should have done it to the power of 12. Yeah, so it's 1 minus that to the power of 12, which, I mean, it's shown here. Okay. To make things simpler, let's consider the case of a healthy person has been given 3 different lab tests, each of which has a 5% chance of yielding a false positive result. 8 combinations of positive and negative results are possible. These various alternatives with the probability that each will occur are given in table 5.4. Now, the probability of any test or combination of tests being positive includes all but the last line. Because all of the other lines include at least one p, we can add up all the lines that have a p, but there's an easier way. The sum of all 8 probabilities has to be 1, so just take 1 minus that. Okay. Which is what this... the same sort of reasoning that I went through. You can see that changing the false positive rate moves the curve up or down, but the basic relationship between the number of tests and the probability of at least one being abnormal stays the same. Just to recapitulate, to figure out the probability of at least one event occurring, we first determine the probability of no events occurring, and then subtract this number from 1. So in addition to learning some stats, you've also learned a lesson in clinical care. Don't order more tests than you really need. What do these statements have in common? Any wire cut to full length will be too short. Any error in any calculation will be in the direction of most harm. If you miss one issue of any magazine, it'll be the issue that contained the article, story, or installment you were most anxious to read. For a bike rider, it's always uphill and against the wind. I don't know, D? Yeah. I was first introduced to this apparent breakdown of the laws of probability when my kids were small and learning to put on their shoes. You'd expect that if they didn't know right from left and put their shoes on at random, they'd get it wrong only half the time. This is not what happened. It seemed that they put their left shoes on their right feet at least 89% of the time. Oh. They got it wrong 89% of the time? Sheesh. Again, a giveaway question, of course. Of course there is. What we're dealing with here is called the binomial distribution. Wait, so the question is now, is there some way to tell how often this deviation from chance would be expected to occur? Okay, hold on. Let's just see how far are we. We're not that far away. We might even go through a bit of chapter 6. Right, where were we? We're here. We were here. I'll go to the toilet for a bit, and then we'll continue. Yeah, yeah. Okay. Right, I'm back. Before we continue, maybe let's play a game of chess. Because yes, I am addicted as always. Wait, what is this again? This is the French? Yeah, it is the French. The French Sicilian. We take and then push? Or... yeah. Knight there, bishop here. Oh god, right, how did I... wait, how did I miss that actually? That's insane. How do I even recover from this? There's bishop here. Which... no, I just can't recover from this. That's insane. Wait. Oh, this is so dumb. How do I deal with... I know everything here is correct. Knight takes c6 is correct, and then bishop d3 is correct. I just don't really know how to deal with d5. Apparently, e takes d is correct instead of c takes. Okay, so the threat is d4. We do e takes. C takes is immediately winning because of queen a4, so I have to be aware of that. E takes, and then we just immediately castle. Okay, so E takes to open up the E file, and we castle. This is not a threat anymore because there's no more pin, and then we have an open E file. Okay. Okay, bishop g5, bishop f4. Okay. Right. course we're playing another game. That doesn't count. First one doesn't count. All theories so far? All theories so far? Let's see. I think this just takes. I'm somehow inclined to think e5, but that just loses a pawn. I think there is like some compensation. I think there is some compensation, honestly. Yeah, if it doesn't work, I'd at least burn down this time. Ooh. I guess here to attack the pawn. C4 is. But I mean, what else are you gonna do? Bishop C4 is. Takes, queen takes, knight takes. This is hanging. I think I have the better pawn structure in the end. Because that C pawn should be a nice target for me. Dude, this guy sure is taking his time. Not that I'm complaining, because higher chance of victory. Dang, okay. I mean, okay, let's defend the pawn. Let's bring our knight here, so that we can activate our bishop somewhat. And then we should be fine. This guy's not gonna win with 5 minutes left on his clock, with the way he's using his time. Not sure where though. Bishop d6 would be good. Like, wait, no. Maybe. No, this would be better. He is, this guy is speeding up. I don't think we have to react to this one at all. Yeah, there's even Queen G4 ideas. Okay, dude. I need to follow up after Queen G4, G3. Oh, Queen takes. Right, so you have to go back. then let's try queen f4 now. Queen f4. Again, this takes queen f4. How else can you? What else can you do? Queen here to ask for a trade. But then just okay. And the 94 should just be like can do knight takes or queen takes. No, queen takes is better. You can just not take the rook, honestly. But let's not be... that's not necessary. This is important. Knight takes, knight, that it also attacks the queen. +3. Okay, maybe knight takes pawn was better. Okay. Okay, I might have screwed up here. Cause rook here. Oh yeah, king there. Oops. This is getting out of hand. Wow. I just have to survive for 1:30. Now just a minute. It's not super easy. Then yeah, push king here, push king takes. You can't just push because my rook's guarding the back rank. Push here. Yeah, okay, hold on. Let me think about this very carefully. Okay, there's bishop there, which is a no-no. Dude wants a draw. Okay. Dude, I actually survived this. How? Dude, I didn't need to flag. Like, this is just a winning position for me. Holy shit. Wait, was I truly okay? No, I'm definitely, like, screwed here. Best move was d8 queen, and then king b8. Like, okay. Like, yeah. You have to... Insane, you have to figure that tactic out. I think it's not hard, but like... with only a couple seconds left. I was... totally winning. What was the best move? Oh, there's queen takes h3 as well. I completely missed that. But yeah, knight takes c3 is better than knight takes rook. Well, very little difference. It is just... Dude, this is... Wow. Okay, but what about this? That's very scary to do. But yeah, there's no way of protecting the pawn, so b6, a takes b, and yeah. Okay, if not b5, because I might be too scared to do that, there is b6, which is almost as good. Or rook fd8. Okay, maybe b6 then. Then b5 is the next best move. Or yeah, maybe just play knight takes from the start, from the get-go. Okay, who's playing knight d4? What about just an immediate e4? That's also possible. Just... Oh, okay. Right. Knight b3 check, rook takes. Oh, yeah. Okay. Anyway, we'll continue. As you know, the called normal curve describes how a continuous variable, such as blood pressure, or IQ would be distributed if we measured it in a large number of people. The curve can also be used to give us the probability of a given event, such as the diastolic pressure 95. However, the examples we just gave are not continuous, but have only two possible outcomes. The wire either will be too short or it won't be too short. The missing issue either will be the one containing the last installment of the mystery story, or it won't be, and so on. What we would like to have is something equivalent to the normal distribution that can be used to both describe and give us the probabilities for dichotomous events. Not surprisingly, we have such an animal. It's called the binomial distribution. The binomial distribution shows the probabilities of different outcomes for a series of random events, each of which can have only one of two values. The music just died. Never mind. Okay, we still have a bit left. Let's start off with the easiest case where each of the two values is equally likely. The usual example used in every other textbook is flipping a coin and seeing how many times it comes up heads in 10 flips. For that reason, we'll avoid that example assiduously and stick with the kid putting on his shoes. If you let the kid try to put his shoes on once, there are two possible outcomes, right or wrong, each of which should occur 50% of the time. If there are two attempts at getting shod, then the possible outcomes are R on both tries, W on both tries, R on first and W on second, W on first and R on second. It's easy enough in this instance to figure out the probability of getting it wrong both times. There are four equally possible outcomes, so one of which is the combination WW, so the chances are 1 in 4. The other way to figure out is to use the multiplicative law. Blah blah blah. Okay. could do the same thing for 3, 10, or 100 tries, but these methods are laborious. For example, we could ask the question, if a kid puts his shoes on 10 times, what's the probability that he will get it wrong on exactly 7 of those tries? We tried to solve this by making a table of the possible outcomes. We quickly get bogged down. On the first try, there are 2 possible results. For each of these outcomes, there are 2 possible results for the second try. Again, blah 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 blah. Yeah. Binomial expansion. Though we're trying to avoid equations as much as possible, this one comes in quite handy, so bear with us. We'll have to define a few more terms in addition to the ones we use in discussing combinations and permutations. P is the probability in each try of the outcome of interest occurring, and Q is 1 minus P. Now the formula for the binomial expansion is this thing. So this is combination, the combination formula, and this is some stuff. Okay. First part should look familiar. It's the formula for the number of combinations of n objects taken r at a time. We can also write equation 510 as this thing, because the term nr is simply a shorthand way of writing that thing. These equations may look fairly scary, but actually they're not hard to handle. The only difficult part is calculating factorials, but nowadays many calculators can do it for you, blah 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 blah. So okay, 10 out of 7, and then 0.5 is the probability. The probability is just under 12% that the kid would get it wrong 7 times out of 10 if you were really putting the shoes on at random. Now let's get a bit fancier. What's the probability that he does it wrong at least 7 times out of 10 instead of exactly 7 out of 10? He's getting it wrong 7, 8, 9, or 10 times out of 10 trials. You just have to calculate all of these and add these things 4 times. Add these 4 things together, don't we? Yeah, just add everything up. Okay. So far we've dealt with situations that have a 50-50 chance of happening, but we're not limited to this. Blah 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 blah. Okay. So the probability that 5 of the 15 patients will develop a hospital-acquired infection is 10.32%. What we've learned in this section is how to extend the binomial expansion beyond the case. Blah 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 blah. Okay. Staying with this example for a minute, how many people with nosocomial infections would you expect to see on our 15-bed unit? It's almost intuitive that given 15 patients and an incidence of 0.2, we would expect that most of the time 3 infected patients would be on the unit simultaneously. In figure 5.2, we've plotted the probabilities of having anywhere between 0 and 15 nosocomial patients on the ward at the same time. This was done using equation 510 by setting r equals 0, then r equals 1, up through r equals 15. Okay. Notice that the distribution isn't quite symmetrical. It's skewed somewhat towards the right. This figure then shows the binomial distribution. Okay. What happens when you change the probability and the number of trials? In this case, each patient can be thought of as one trial. In figure 5.3, we've kept n as 15, but we've changed p from 0.2 to 0.3. What happens when you change? Okay, yeah, okay. You would expect that the average number of the word at any one time would increase, and sure enough, the graph has shifted to the right a bit. It also looks as if the data are spread out some more, and there's a bit less skew. If we keep p at 0.2 but increase n from 15 to 30, we would again expect a shift to the right with an expected average of 6. Miradibel dictu. The data behave just as we predicted, and again there seems to be a greater spread in the scores. So let's summarize what we've seen so far. First, as p gets closer to 0.5, the graph becomes more symmetric. When it is exactly equal to 0.5, the graph is perfectly symmetric. When p is less than 0.5, the distribution is skewed to the right. It's skewed to the left when p is greater than 0.5. We haven't shown that, but trust us. Second, the closer p is to 0.5, the greater the variability in the scores. Third, there isn't just one binomial distribution. There's a different one for every combination of n and p. We learned in the previous chapters how to figure out mean, SD, and variance of continuous data. We can do the same for binomial data, and thus numerically describe the properties of the binomial distribution that we just saw graphically. As we would expect from the graphs, these properties would depend on n and p, and therefore also on q, which you remember is 1 minus p. What we have then is that. We go back and compare figure 5.2 with figure 5.4. It looks as though increasing the sample size with the same value of p makes the graph seem more normally distributed. Yet again, your eyes don't deceive you. As n increases, the binomial distribution looks more and more like the normal distribution. Let's pursue this a bit further. In figure 5.5, we show a normal distribution with p equals q equals 0.5. The left graph is for n equals 5, the middle shows n equals 10, and the right part shows n equals 20. So these are, yeah. As you can see, the graph looks more and more normal as n increases. By the time n equals 30, the graph figures virtually indistinguishable from the normal distribution. What this means is that if we're dealing with binomial distributions where n is 30 or more, we don't have to worry about using equation 510 to figure out the probabilities. We can approximate the binomial distribution by using the normal curve. In fact, when p equals 0.5, we can use the normal curve when n is as low as 10. However, the more p deviates from 0.5, the worse the approximation to the normal distribution. So using the normal curve only when n is at least 30 is fairly safe. To illustrate how you can use the normal distribution to approximate the binomial one, let's stick with an example of patients who leave the operating room minus an appendix but with an infection, and we'll figure out how likely it will be that we'd have 5 such people on our unit at one time. Now, one difference between the normal and binomial distribution is that the former is intended to be used with continuous variables and the latter with discrete variables. Consequently, we have to consider the discrete value of 5 people as actually covering the exact limits of 4.5 to 5.5. next step is to convert these two numbers to standard scores, checking the... Okay. Okay. Recap. In this chapter, we've looked at the nature of probabilities and explored figuring out blah 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 blah. Okay, I just skimmed through that, but let's figure out the let's figure this one out. On our own. I'm gonna grab my thing for writing stuff. It working? Yes. Okay, hold on. Let me change scenes. Alright, so the question is, we have 73 white marbles and 136 black marbles. Now we want to so you took out 12 marbles, replacing each one after you took it out. Okay, right, so this is just, so if we let x be the number of white marbles you observe, so x can be 0, 1, 2, 3, all the way up till 12. Now we're just interested in seeing 5. So it will go up to 5, and then we'll have that up till 12. And now we have the probability of x occurring, and then we just have to figure this thing out. Basically, x can be thought of as the number of successful attempts, successful trials, successes. And the success will be when we take a white marble out. So we need 5 successes. So the probability of success here is just 73 divided by 136. And then to do this, we just have to do the let me look at the formula. Right, so that's n factorial over r factorial n minus r factorial pr q n minus r. N is 12. That's 12 factorial. R is 5. So 12 minus 5 is 7. P is 73 over 136. There are 5. Then Q is, well, 1 minus that, which should be 57 plus 6, which is 63. To the power of 7. Right, so if we just calculate this, we should get the right answer, hopefully. Hopefully. Okay. I'm just plugging everything into a calculator now. And I get 8%. So if we were to go here, Okay, that's exactly what I wrote down, yeah? Hold on, I need you to... Okay. Cool. So... I guess that's probability done? Question mark? Don't really feel like doing any of these. Anyways, now this is where the fun starts. Elements of statistical inference. But we'll save this for another time. Because this is where the actual statistics are occurring. And this is a pretty long chapter. They talk about key distribution. Yeah, we'll figure all of this out later. They talk about like Cohen's D, stuff like that. Oh, she's literally right here. Okay. Cool, this should like be sufficient for what I'm trying to do, hopefully. Okay. Okay. Well, I'll see you later, I guess.